Welcome, kids, to equations of planes. Our last video was on equations of lines in 3-space. So now we're going to work with an equation of a plane. So here is just a sketch of a nicely, variety colored plane there in kind of a first octant of 3D space. And notice that there is a, kind of like a spear going right through it. And that is because a plane in 3D space is determined by this point on a plane and a vector that is perpendicular to the plane. Now, this point could be anywhere, and because if the vector is perpendicular to one point in a plane, well, then it's perpendicular to, any of the points in the plane. This vector is called the normal vector. So how to find the equation of a plane. So this is kind of a sorry drawing, but sorry. I have this point here that is fixed. P sub 0 is a fixed point. And this is any other point on the plane. From the origin, the position vector r sub 0 goes from the origin out to the fixed point of the plane. And the vector r goes from the origin out to any point on the plane. Right, so take a moment to convince yourself that this red line that lies within the plane is r minus r sub 0, or you can think negative r sub 0 and r, right? Get you across there. This more solid red line is my normal, right? It's gonna, maybe if it goes all the way through. Right through the plane, right? And it kind of nails down that plane in space. So there's our fixed point, the normal with horizontal component A, x component A, y component B, and z component C. And then any point, x, y, and z is that random point on the line. R sub 0 and r are the position vectors. And as I said, r sub o minus r is the vector that goes between those 2 points. Since n is perpendicular to the plane, it is perpendicular to any vector that lies in the plane, right? You can think of all the lines being coplanar. And remember that 2 orthogonal or perpendicular vectors will always have a dot product of 0. So that means that n, the vector n, dotted with, oh, that's terrible. Right, that dot product is 0. N dotted with that line r minus r sub 0 in the plane. Now, if you remember from, may or may not remember from properties of the dot product, this is, n can distribute across those. And if n distributes across those, you would have nr minus nr sub 0 is equal to 0, and then you just move this over to the other side, and boom, you have this equation. That's actually an equation of a plane. It's just not super useful. It's called the vector equation of the plane. Don't use it hardly at all. Can't remember using it. More useful to us than the vector equation of the plane is going to be the scalar equation of a plane. So starting with the normal vector and the line in the vector in the plane, and that they are perpendicular to one another, therefore their dot product is 0. I'm going to expand that. So n, remember, is a comma b comma c, and then r minus r sub 0, right? It is just x, y, and z of any point on the line minus the x, y, and z of my fixed point on the line. I'm going to use my properties of how to subtract vectors and get one x component, one y component, and one z component, and then I'm going to do the dot product. I'll check out what I've got there. Look at that. That equation of a plane, I see, get it? I see.
I could not get it to work.
I see the components of the normal vector. I also see the coordinates of the fixed point in the plane. So for an example 1, let's find an equation of a plane through a fixed point 2, 4, -1 and the normal vector 2, 3, 4. I want you to find the axial intercepts and sketch the plane, right? This is really a no-brainer. You kind of sort of think of this as point slope. 2, 3, and 4 are your A, B, and C. 2, 4, and -1 is the point on the plane. A, B, and C, multipliers, x minus the x coordinate 2, y minus the y coordinate 4, and z minus the z coordinate -1 equal to 0. Bam! Done and done. We do a little algebra. Distribute and combine, right? So I got 2 minus -2, 3 times -4, and 4 times +1. Combined all those together to get -12, and then I move the constant to the other side and put it here. The reason I did that, firstly, that's called the standard form of the scalar equation of a plane. And whoops, secondly, that's easiest to find the axial intercepts, right? The actual axial intercepts. Where does this plane hit the x-axis? Well, it's when y and z are 0. So wouldn't x be equal to 6? Where does it hit the y-axis? Well, that would be when x and z are 0. How about the z-axis? When x and y are 0. And then no judging my drawing. Over here, I'm going to try to draw. X is 6. Y is 4. And z is 3. Draw the traces. The xz trace. Oh, it's so terrible. The xy trace. And the yz trace. And there is the image of the plane as it comes through, right, that first octant. Up here, I've got a link to a GeoGebra picture of this. Come on, computer, you can do it. This was a long wait for something that's not all that impressive. It's just a picture of a plane. But I did use this one sketch. I'm going to demonstrate something with example 1 and another example that we use. So I guess it's worth the wait. I probably have it over here. Yeah, I know it's unresponsive. Ah, finally. All right, look at what I have up here. Equation 2x plus 3y plus 4z is equal to 12. Here's that plane. Right? Can you see it? Look, do you see the triangular kind of shape there? Right? Axio-intercept 6, axio-intercept 4, axio-intercept 3. Right? There's that plane as it comes sweeping down through. Right? Kind of cool. Right? Notice you can see, right, the intersection, what the shape looks like there as it goes through the plane of the coordinate axes. Oh, looky there, right? I'm going to come back to this drawing. In a little bit. But from here, so there's my pathetic drawing. Ha ha ha. So if I kind of do the algebra that I just did, but in general, instead of actually putting values of A, B, and C and putting the particular point in there, what if I go ahead and just do the distribution and collection? And notice that what I did, remember, this is going to be a number when I actually put in values. This is just a number, right? Because it's a particular x. This is just a number. This is just a number. If I combine all of those together and move them to the other side, and then if I actually, right, add them and get, for instance, like I got a negative 12, or I'm sorry, a 12 by the time I moved it to the other side, this is the standard form, most common form of the equations of planes. And it is called the standard form for the equation of a plane. Notice again that when you distribute, I maintain the normal vector. I can see the normal vector. Right, there's the normal vector, A, B, and C. But with this distribution and combining all the constants over here in D, I lose the particular point that I get when I'm kind of in this more point slope-ish kind of formula. So example 2, determine the equation of a plane, and I'm asking you to put it in standard form, that contains these 3 points, because remember, 3 non-collinear points determine a plane. Well, I want the equation of the plane. So step 1, remember, if I'm going to write the equation of a plane, I need I need the normal vector and I need a point. Well, I've got 3 points, so that's cool, right? I can use any 3 of these points, but I need a normal vector. Well, to get a normal vector to the plane, I have to kind of sort of create at least 2 vectors that lie in the plane. Then find their cross product to find the normal vector. Then I use one of the given points and I'll write the equation in standard form. So let's do that work. So the first thing I'm going to do is write the equation of write the vector PQ. Remember, PQ would be 3 minus 1, negative 1 minus 3, and 6 minus 2. Then I'm going to do PR. PR is 5 minus 1, 2 minus 3, whoops, and 0 minus 2. Okay, so I've made these 2 vectors kind of, sort of, right, so that they meet at point P. Right, they meet at point P, and one is Q, one ends in Q, one ends in R. So now I'm going to find the normal to those 2. Right, I'm going to find Got to imagine that coming. And remember, I draw it through the point. Doesn't necessarily have to go through the point there. But to find the normal, that's what we did. We did the cross product, right, in the previous video. So the cross product is the determinant of a 3 by 3 matrix where the first row is I, J, and K. Right, so it's I times 8 minus negative 4, J, negative J times negative 4 minus 16, and K times negative 2 minus negative 16. So the normal vector now you remember why that 20 is positive, right? We went through this, the derivation of why the J is negative in the previous video. Now I'm ready for my standard form, right? I adjust my standard form of my equation in kind of the distributed form. A times x minus the x coordinate, b times y minus the y coordinate of a point on the plane, and pick any point that you like. I will just pick the first one, 1, 3, and 2. And I get 12x minus 12 plus 20y minus 60 plus 14z minus 28. This is all negative 100 or minus 100. Add to the other side and I get 100. If you want to divide everybody by 2 to make your coefficients smaller, that's fine, but you don't have to. So let's go back to that GeoGebra and look at what I've done. Turn off this plane. So there's the 3 points, right? 3 random points in the plane. 3 random points in space, but 3 points determine a plane. So the first thing I did was create the vector PQ. Then I created the vector PR, right? And then I did the cross product to find the normal to those two, and then filled in my formula. And I got 12x plus 20y plus 14z is equal to 100. Bam. Right? Look at that. There's the plane that contains those 3 points and its equation. Its equation is 12x plus 20y plus 14z is equal to 100. Oh, snap. All right. A formula to find the angle between 2 vectors, right, is the dot product of the 2 vectors divided by the product of the magnitudes of the separate vectors. Well, hopefully it won't be too much of a surprise to find that the angle between 2 planes involves their normal vectors, right? So the angle between 2 planes is the dot product of their normal vectors divided by the product of the magnitude of each one of those normal vectors. 2 planes are parallel if their normal vectors are parallel. So I have this little clip art of a book, right? And that book is not flat, right? The book it's bent. It's got a little bit of a V. If you imagine a vector that is normal to this side of the book, right? And it would go through. The vector that goes through this side is not parallel. Those 2 vectors are not parallel. However, can you imagine that if you laid this book flat, that those 2 vectors would both be pointing directly up or directly down, and they would be parallel. which means kind of like thinking of the one side of the book as plane 1, and this is plane 2. Okay, distance. Distance between a point and a plane. Now, somebody may have just handed you some formula in pre-cal, but here's what that formula, and maybe you remember it, maybe you don't, maybe you were never given it. But the distance between a point and a plane, given that you have that you know a point, you know a point here with it's fixed on the plane. You know a normal to the plane, right? Now this vector goes on forever and ever and ever, right? And then you have vector B. Vector B goes from up the fixed point on the plane, up, out, over, down, wherever this point in space is, off of the plane. So the length of vector B is not the distance from the point to the plane, right? Because distance is defined to be the shortest distance. So capital D for distance is the length of this piece of the vector, right? Because that normal vector goes on forever and ever and ever and ever, right? I just want this piece of the normal vector, and I want to know how long it is. I just want to know the length, a scalar, of this side of that right triangle. Well, remember our projections from before? The projection of B onto that normal, right? Remember, here's our spotlight shining down on B, right? And this line, the projection down on the normal, right? Technically, there's spotlights all over, right? This looks like a bunch of jellyfish. I am the worst drawer. But if you imagine the shadow, of vector B projected down on the normal, I need the length, which is the scalar projection of B onto N. And remember, we say that's the component of B upon N. Right? And that is a number. That number is this distance. So what's the formula for the component? Do you remember that from yesterday? The formula for the component of B onto N, and remember, I want a positive value, right, is a distance, is the dot product divided by the magnitude of where your shadow is. The dot product of where the shadow is, the vector where the shadow is, with the vector that is you're doing the projection of. So what does that look like? Right, our normal vector is A, B, and C. And here is vector B. Let's do that distribution like we did before. Now remember, be careful. There's no equation up here. There's no equation up here, so be careful about that equals D. Right? Be very, very careful. This D is not the same D as that formula. It's on t'other side. I already have an equation. I can't have the standard form of an equation and have equals D here, right? The standard form is AX plus BY plus CZ is equal to little d. Well, this is a particular X, Y, and Z, right? Particular X, Y, and Z of where I want of a point in the plane. And then this D has to be moved over here. Now, I know some people get freaked out by, they're like, how can you put a plus D? You change signs, it should be a minus D. I mean, D can be positive or negative on either side. Of course, I would change right? I would negate it. if I was actually switching the value. But you just need to know that this value in the distance formula for the distance between a point and a plane, which does have a Pythagorean component to it, right, really is you are actually finding the length of the projection of the vector that goes from, that connects the plane to the point off of the plane. Vector point on plane to point off plane, right? So let's do a quick example of that. Find the distance from the point 285 to this plane. So the first thing you need to recognize is there's your A, there's your B, there's your C, here's your X sub 1, Y sub 1, Z sub 1. So you're going to get 1 times 2 minus 2 times 8 minus 2 times 5 minus 1. Do you see that? It's a trap. Be careful. Oh, R.I.P. Admiral Akbar. Loved him. Anyway, there is, right, be careful. This is a 1 on the right side of this equation. I can't use the equation. I have to just use the expression. I have to put an expression into the distance, that distance formula. So the expression needs to have this 1 moved over, and I need to be equal to 0. Okay, so it is a minus 1, right? Minus 1 divided by the square root of 1 squared plus negative 2 squared plus negative 2 squared. Now this ends up to be a negative number, so I need these absolute value signs, right? Because this is 2 minus 16 minus 10 minus 1. So that's negative 25. Take the absolute value of it, though, and I get 25 thirds. All right, next. Find symmetric equations, ew. I don't like symmetric equations, for the line L of the intersection of these two planes. Pink and blue. Right, so two lines meet, they meet in a line. And I want to find the equation of that line, and I want it to be in the symmetric form. So there's a symmetric form. Don't know why I have random period there. But remember, A, B, and C are the components of the normal to line L. Since L is in both planes, it is perpendicular to both normal vectors. Does that make sense? Think if that makes sense. Right? Therefore, when I do the cross product of these two normal vectors, I will get a vector that is parallel to L. And parallel to L, as long as I have a vector parallel to L, I can get A, B, and C. I said normal up here, but I don't mean normal. I meant parallel. Then to find a point on the line, I'll find out where L intersects one of the planes, right? I pick the XZ plane and I'll make Z equal to 0. And I just thought that would be easiest to do up here. In both of these equations, I'll make Z equal to 0. Whoops, sorry. So let's do some work here, and then I'll show you a GeoGebra picture of this. All right, so the first thing I want to do is find the cross of the, right, because I have a normal vector normal vector in the red. There's my normals, 1, 1, and 1. So normal pink. And normal blue. So when I find pink cross blue, pink normal cross blue normal, right? I is 3 minus negative 2. J is 3 minus 1. And K is negative 2 minus 1. Therefore, a line parallel to L right? So now I have a line that's parallel to L, but I want it to go through the point 1, 0, 0. And where did I get that point again? Right? I want to see where does this plane hit, right, a point on the line. So what I did was I made z equal to 0, and I had x plus y is equal to 1, and x minus 2y is equal to 1. I solved the system. I subtracted. X minus x is 0. Y, 1y minus 2y. I'm sorry, 1 minus negative 2y is 3y. 1 minus 0 is 1. Ah, this was a 1. 1 minus 1 is 0. Therefore, y is equal to 0. If y is equal to 0, what is x? X plus 0 is equal to 1, so x must be equal to 1. And I already chose z to be equal to 0. So there's my A, B, and C. So the symmetric form of the line would be minus 0, minus 0. All right, let me show a little bit. That was a lot of seemingly rambling math. Let's look at this. Here is the pink and the blue planes, right? Pink and the blue planes. There they are. And then can you see the line of intersection, right? Can you see the line where they cross, where they meet? Right? Here is the vector that is normal to the pink. Can you see that? That vector is normal, perpendicular to the pink. This is the vector that is perpendicular to the blue. Right? And I just got those from the coefficients, right? 1, 1, 1. The coefficients of the variables in standard form are the components of your normal vector, right? So So those two, since those two lines are perpendicular, right? They are normal to these two planes. And this is what I was saying before, then the cross product of those two will be parallel to the line between them, right? I hope that visualization helps a little bit. Now, here's the point 1, 0, 0 that I found setting z equal to 0 and then saw it getting that system. Can you see there? That's the point 1, 0, 0, A. And hopefully you can tell that that is on the line of the intersection of those two planes. So using that point 1, 0, 0, and then the cross product of the two normal vectors, look at what I got. There's the equation of the line, the intersection of those two planes. Right, now that's not symmetric form. But I think that you're able to get symmetric form from that. All right. That's it for the second day of 12.5. I will see you soon.